Alright, in this next section, we're going to discuss polynomial functions and models in general. Previously, in our previous topics, we talked about leading coefficient, we talked about degree, and we're going to see exactly what those two things tell us about polynomial functions. Alright, so far we have talked about extrema. That was one of the first things we talked about in this section, in this module. And remember, extrema, this is just another term that we use to discuss the highest and lowest points on a graph. Remember that extrema can be absolute, meaning it is the absolute highest or absolute lowest point of the graph. Or they can be local, which means that they are just the highest or lowest points in their area. So remember that we've talked about minimums, maximums. We sometimes refer to these as extrema when we want to think about them at the same time. And we actually have another term that we use for extrema, as if we don't have enough. We call them turning points. This is another term for all extrema. Local, absolute, and we call them turning points because these are points where the graph switches from increasing to decreasing or decreasing to increasing. All right, so these are things that we've already talked about. The next thing that we are going to talk about is end behavior. End behavior, what this basically tells us is what happens to a graph as it approaches positive or negative infinity. What happens on the far edges of our function. In order to determine end behavior, we want to look at the leading term, and remember that this is the term of highest degree. The leading term we saw had two things in it. It had a coefficient, which we called the leading coefficient, and then it had the degree. When we talk about degree, we have two possibilities that we're going to consider. The first one is if the degree of the polynomial is even. This means the largest exponent. If the largest exponent is even, we have two possibilities. If our leading coefficient is positive, then the graph goes up as we approach negative infinity, as we go to the far left of the graph. And it also goes up as we approach positive infinity. This is going to be the book notation. And obviously you're going to need this when you're doing your homework and the quizzes. But this is basically what it says. F of x, the y's, approach positive infinity as x approaches negative infinity. Meaning as we go to the left, we go up. We have and f of x approaches positive infinity as x approaches positive infinity. Meaning that our graph goes forever up to the right. Now, the notation that I do recommend you use, because it's a lot easier to think in terms of this, is we have something that looks like this. We have an arrow going up to the left, we have an arrow going up to the right, and this is our shorthand notation. Notice that there's a gap in between, because what we're going to see as we look at these problems or these examples in this video is there can be all sorts of stuff going on in the middle. But we always know that as we go forever to the left, we're going up, and as we go forever to the right, we're going down. An easy one to think about that we'll look at in a minute is think about quadratics. Quadratics have an even degree, And we know that if our leading coefficient is positive, it's a quadratic that opens up. If our leading coefficient is negative, it opens down. And this extends to any polynomial that has a highest degree that is even. All right, so let's talk about what that means. Okay, if the leading coefficient is negative, and we still have that our degree is even, then the graph goes down as we approach negative infinity, and it also goes down as we approach positive infinity. All right, our book notation. This is saying that f of x goes towards negative infinity as x goes towards negative infinity. And f of x goes towards negative infinity as x goes towards positive infinity. And so what all this terminology here means is that as x goes to the left, y goes down. As x goes to the right, y also goes down. We also have a shorthand notation for this. Instead of having arrows that point up and up, we have arrows that point down and down. So down and to the left, and we also have down and to the right. All right, these are our even polynomials. Note that these are polynomials with an even degree. Let me change that. I don't want us to get confused in terms of symmetry because that's a completely different thing. All right, so now the second thing that we have is what if the degree is odd? And so if we have the degree of the polynomial is odd, so think like even linear functions, it is technically an odd degree polynomial. Cubic functions are also an odd degree polynomial. We also have the same conditions. We need to know what happens if the leading coefficient is positive. If the coefficient is positive, what we have is the graph goes down as we approach negative infinity, and it goes up as we approach positive infinity. So think about a linear equation that has a positive slope. If it has a positive slope, it is increasing from left to right, which means that on the left side it goes down forever. On the right side it goes up forever. All right, we have our book notation for what does this mean. So we have f of x goes towards negative infinity or down as x goes to the left. And f of x goes towards positive infinity or up as x goes towards positive infinity or the right. The shorthand notation we can use is we have an arrow pointing down to the left. We have an arrow pointing up and to the right. And again, lots of stuff can happen in the middle. All right, and the last thing that we have is if the leading coefficient is negative and our degree is still odd. Then what this does is it goes up as we approach negative infinity, and it goes down as we approach positive infinity. All right, so our book notation. This is saying f of x goes up as x goes left, and f of x goes down as x goes to the right. We have our shorthand notation, and an easy way to write this is we have an arrow pointing up and to the left, and we have an arrow pointing down and to the right. All right, so what we're going to be talking about in this section is we are going to be, first off, talking about the relationship between the degree, the x-intercepts, and the turning points. We're also going to be talking about end behavior, and we're going to apply this to analyze equations and graphs. All right, the rest of this video is going to be designed to basically look at all of our polynomial functions from the most basic up to, I'm not going to say the most complex because they do keep going, but we're going to go ahead and increase our difficulty level. The first polynomial function that we have is the constant function. Remember that the constant function has no variables. It is just a number. Since there are no variables, we have a degree of 0. Now, we're not going to consider f of x equals 0. That one kind of throws off the whole thing. But if you have f of x is equal to any number other than 0, you have no x-intercepts. It is a flat line, which means that it's not increasing or decreasing, and so you can't have it be both. So there are no turning points. We are not going to talk about end behavior for this one. This is the only one that we don't talk about end behavior because it is a flat line. We're never increasing and we're never decreasing. All right, if we go ahead and look at some graphs of this, well, there's basically only one that we consider. It's a flat line. It's either going to be above the x-axis or below the x-axis, but they all look the same. All right, this is our first one. Okay, so let's increase the difficulty level. The next thing we're going to do is talk about a linear function. Linear function in standard form is going to be f of x equals ax plus b. And we're going to not use m because m is when we're just talking about linear equations. We want to kind of be specific when we talk about, we're going to kind of be general in terms of what we're going to label the coefficients as so that we can kind of see the pattern. So we have f of x equals ax plus b. We want to know, first off, what is the degree? The degree, we have 1x. This is my leading term. We have 1x, which means that my degree is 1. We want to know how many x-intercepts do we have. And, well, no matter what, if we graph a linear function, we basically have two options, okay? Our first one is, it's an increasing line, or it's a decreasing line. And these lines can be anywhere on this graph. But the important thing is, no matter what, we will always have a single x-intercept. All right, so every linear function that has a slope that is not 0 has one x-intercept. Because linear functions are either strictly increasing or strictly decreasing, we have no turning points. Remember, turning point is going from increasing to decreasing or vice versa. All right, we have our leading term. We have two possibilities again. We have two possibilities for leading term. We have a can be greater than 0, or a can be less than 0. The first graph over here, this is a is greater than 0. And so notice if we just focus on the very ends of this graph, we are going down and to the left we're going up and to the right. And so every linear function that has a leading coefficient that is positive is going to be of this shape. Our second graph is if we have a negative slope. And so our leading coefficient would be negative. And so, again, we do the same thing. We just want to pay attention to what happens at the far ends, the end of our graph. And what we get is this goes forever up and to the left, and forever down and to the right. I don't want to focus a lot on the book notation, but I do want to give you a couple of examples so that you know what it should be. So what we have here is f of x goes towards negative infinity as x goes towards negative infinity. I'm going to do the first one. Okay, this is just saying the y's go down as x goes to the left. We do have to also include the second part of this. We have f of x goes towards positive infinity as x goes towards positive infinity. And so this little arrow right here, the one on the left, that's the first statement. The arrow on the right, that is the second statement. And if you want to do the other one, well, then we just need to flip our infinities around on our f of x's. All right, so these are the first two that we have that are technically polynomial functions. Okay, now we're going to get into ones that we kind of think more of as being polynomials. But we're going to still start out with something that we are familiar with. The next one that we're going to look at is quadratic functions. And so quadratic functions we know is ax squared plus bx plus c. We want our largest exponent for our degree, and our largest exponent is 2. So our degree is 2. All right, now when we talk about number of x-intercepts, keep in mind that we're talking about all quadratic functions. And we can have several possibilities. And we've talked about these in previous math classes, in previous sections. And so let's look at some graphs. All right, the first one we have that we're most familiar with is we have a quadratic function that looks something like this. And we have 2 x-intercepts. So that is our first possibility. We can have 2. But this is not the only possible quadratic equation that we can draw. When we talked about transformations, we also talked about just doing a horizontal shift. And when we looked at these ones, we had that it touches, we'll get into that later, but it only has 1 x-intercept. And so that is also a possibility. But we still have one more. We have one more possibility, and the last one is we talked about graphs that never touch the x-axis. And so it's possible to have 0 x-intercepts. All right. We want to know how many turning points do we have. So remember, turning points is where does it go from increasing to decreasing or vice versa. And so if we look at all of these graphs, we have a decreasing down to the vertex, and then they turn back around and they are increasing away from the vertex. And technically, I just drew examples that open up, but note that you can also have quadratic equations that open down that still have two x-center steps, that still have one x-intercept, or have no x-intercepts. And when we talk about these, we do still have the same idea. We are increasing on one side of our parabola. We're decreasing on the other side. And so when we talk about quadratic functions, every quadratic function has one turning point. It has a vertex. Every quadratic function has a vertex, and it's a maximum or a minimum, which is another word for extrema, which is another word for turning points. All right, we have possibilities for our leading term. And so we do still have A can be positive or A can be negative. And so when we talk about positive, when it's positive, remember it opens up. So we're looking at this graph, we're looking at this graph, we're looking at this graph. And if you kind of ignore the stuff in the middle, what we basically have is something that looks like this. We go forever up on the left side, we go forever up on the right side. If A is negative, then we have the other graphs. We have that it opens down. And if it opens down, we have down and to the left, down and to the right. All right, let's do one of these with book notation. Okay, so I'm going to go ahead and do the second one with the book notation. So in book notation, what this is going to look like is f of x goes towards negative infinity. It goes down as x goes towards negative infinity. Goes down and to the left. We have the other side, which is going to be f of x heads towards negative infinity as x approaches positive infinity, which means that it goes down and to the right. All right, these are our quadratic functions. Now, the rest of the examples that I'm going to do is I'm not going to draw out every possibility because there is a lot, okay? But we're going to go ahead and play around with them a little bit to get a basic idea of what we're looking at. All right, the next one we're going to look at is a cubic function. All right, so let's see what we have here. We have that our degree is 3. We want to talk about turning points and x-intercepts. All right, unlike our quadratics, where we basically have just one shape that we're just kind of moving around, stretching, shrinking, flipping, when we get to cubics, we start having more possibilities. And so I don't want to draw out every single possibility, but I do want to kind of play around with two basic shapes when we talk about cubic functions. Okay, so we're going to start off with our coordinate axes. And And we talked previously about our basic cubic function. And remember, our basic cubic function kind of has this snake shape where it comes in, it levels off, and then it continues going. All right, so now we're going to take this shape and we're going to put it on our graph. So I can put it here. And how many x-intercepts do we have? We have 1. Now I can take this same shape and I can move it wherever I want. So for instance, if I move it left or if I move it right, no matter what, I still have that 1 x-intercept. But we can also move this up and down. And if we move this up and down, notice that we still have 1 x-intercept. If we move it up, we still have 1 x-intercept. And so this is our first cubic example. And our cubic is always going to have at least 1 x-intercept. All right, so that is our first example. We have degree 3. We can have 1 x-intercept. Okay, and then now we're going to go ahead and talk about, okay, what's another shape that we can see? So our next shape that we're going to look at is we are going to have something that looks like this. Okay, and we're going to do the same thing. So we're going to kind of play with this basic shape, and we're going to move it around. So for instance, I can put it here, and I do still have an x-intercept. I can move it here, still an x-intercept. We can also do something like this. And if we look at it like this, how many intercepts do we have? Well, for this configuration, we have 2. We have an x-intercept at the origin, and then we have that second one on the right side. And even if we move this around, we still have 2. If we move this picture left, right, we still have 2. We do have one more possibility, and let's say we move it like this. And again, it can be any configuration right here. But if we have it like this, then we do have 3 x-intercepts. And so that is going to be our possibilities for a cubic function. We can have 1, we can have 2, or we can have 3. All right, the other thing that we want to talk about is turning points. So I'm going to bring back my other cubic function. And so our other cubic function, remember, was it goes up, levels off, and then it keeps going up. All right, now remember, turning points is where we go from increasing to decreasing. All right, if we look at the original one that we talked about, if we talk about increasing and decreasing, what we have here is it's increasing. It levels off, but it never actually gets flat for an extended period of time. And then it keeps increasing. And so what we have here is we can have 0 turning points. Now this type of shape that we see, where it comes in, it levels off, and then it takes off again, we do have a special name for this, and we'll talk about it later. But this is not a turning point. All right, if we look at the second option that we had, is we want to know what do we have here. So if we start on the left, we're going up, We get to this point at the top of our peak, and then we turn around and we go back down. And then we get down to that low point, local minimum, and we turn around and we go back up. And so for this one, what we have is 2 turning points. That is our possibilities. We have 0 or 2. There is no cubic function that will have just one turning point. Why is that? Well, that has to do with end behavior. All right, so just like before with our linears and our quadratics, we do have sign of leading term. And so we do still have A can be positive and A can be negative. Both of these examples here are for when A is positive. The first one was just an x cubed. And again, when we talk about end behavior, note that we can do whatever we want in between. It can be all crazy. But when we talk about end behavior, when A is positive, is that we do still have these 2 branches here that are always going to be the same. So if A is positive, we have down and to the left, up and to the right. If A is negative, well, let's take our original one that we had here. And what we can do is we can flip it. I'm going to try to rotate it. Oh, that's not what I wanted. I'll just draw another one. We can flip it. So we can do a reflection across the x-axis or the y-axis. It doesn't matter, okay. But we would get this basic shape here. And if it looks like this, then what we have is we are going up to the left, we are going down to the right. And so our end behavior would look like this. Notice that this is the exact same thing as what we came up with for linear functions. And so when we talk about these, even and odd degrees, linear functions, cubic functions, power of 5 functions, they all have the same end behavior. Just like x squared, x to the 4th, x to the 6th, they all have the same end behavior. The only thing that changes is what happens in the middle. All right, for this one, we're going to go ahead and do a book notation. And I'm going to do the book notation for the second one. All right, our book notation for this one is going to be f of x goes towards positive infinity. It goes up as x goes towards negative infinity, or to the left. We also have the second half of this, which is f of x goes towards negative infinity, or it goes down as x heads towards positive infinity, or as x goes to the right. All right, these are the next 2 that we have. We have our quadratic and we have our cubic. One thing to note is that I do want to mention, sorry, before we move away from our cubic, is we cannot have one turning point on this. Because if you have one turning point, then basically you're saying you are going to be increasing and then decreasing. And that's it. We can't do that. We have to have another turning point in order to have the end behavior that we want. All right, let's go on and look at a couple more. All right, we're going to look at two more basic polynomial functions. Then after that, they get really complicated. And even as we see these ones, we're going to see that they get rather complicated. When we looked at linear functions, we only had basically one basic shape. When we looked at quadratic, same thing, we had one basic shape. When we got to cubics, we saw that we had two basic shapes. And as the degree gets larger, the number of basic shapes that we're going to run into increases quite a bit. So let's start with our quartic and then look at some graphs of quartic functions. All right, so the degree for a quartic function is going to be 4. Okay, now we want to go ahead and look at some graphs so that we can see how many x-intercepts are possible. All right, so let's go ahead and start with a basic graph. And we have quite a few possibilities. So I'm going to go ahead and drag my first one over. And so our first one is going to look like this. It looks similar to a quadratic, except for it gets steeper a lot faster. And then as you get closer to 0, it has a much more defined flat spot. And so if we go ahead and position our graph like this, notice that we have one x-intercept. And again, I can move this around my graph as much as I want, but we still have that one x-intercept. We can also move this above the x-axis, and we have 0 x-intercepts. Or we can move it a little bit below the x-axis, or as much as we want below the x-axis, and we have 2 x-intercepts. And so that is going to be our first option, or our first options, is that this particular configuration can have 0, where it's above the x-axis, 1, where that middle point is on the x-axis, or 2. For this, we also have one turning point. We are decreasing, and then when we get down to that lowest point, we're increasing. And so we have one turning point. All right, now we have more configurations that we can look at. And so the second configuration that we're going to look at is going to be one like this. All right, this one, again, we can have it above the x-axis, and we have no x-intercept, so we still have 0. We can also move it down. And if we move it down, and this is not a great picture, those should be level, we can have 2 x-intercepts. Again, not a great graph. All right, we can move it further down, and we have 3 x-intercepts. Or we can move it to where that x-axis is in between this, and we have 4 x-intercepts. The other thing that we have is turning points, and so for this particular configuration, we're going down and then back up, so there's one turning point. We're up and then back down, that's a second turning point. And then we have going down and back up, we have 3 turning points. All right, so for this particular configuration, again, we saw that we could have 0, 2 x-intercepts, We can have 3 x-intercepts. And we can have 4 x-intercepts. For this particular example, we also had 3 turning points. Okay, now there are 2 possible graphs so far. All right, we've got one more, or we've got another one. And our next one is going to look something like this. All right, so if we look at this particular configuration, notice that we can have 2 x-intercepts. We can also have 1 x-intercept, or we can have no x-intercepts. All right, so that makes no changes to our number of x-intercepts. But we do have a change in the turning points. And so notice as we look at this graph, we are decreasing, and even though we level out, we never actually stop decreasing. But when we come down to this bottom point, we start increasing. And so our possibilities for turning points is 1. Okay, that is this particular one. We do have one more configuration. Our last configuration is going to look like this. It's kind of similar to the one above it, except for instead of those 2 bottom points being level, they can be at different levels. And if we play around with this, it is possible to have 0 x-intercepts if the whole thing is above the x-axis. It's possible to have 1 x-intercept. It's possible to have 2. It's possible to have 3. It's possible to have 4. And then we're back to either 3 or 2. For this one, we have 3 turning points. We are going to start by going down, and then we turn around and go back up. There's our first turning point. We go up, and then we turn and go down, so we have another turning point here. And then we have a third turning point right here, going down to up. And so those are all of our possible configurations. Now, of course, our pictures can be a little bit different. So, for instance, on this last one, we might have the higher point on this side and the lower point on this side. We could reflect it. Same thing with all the other ones. So this is what we have. We did not see any examples where we have 2 turning points. We didn't see any examples where we have 0 turning points. And so when we talk about a quartic function, the number of turning points is either going to be 1 or 3. Just like with our other functions, we do have a leading term that can be positive, or a leading term that can be negative. And so if it is positive, which all of the examples that I drew had a positive leading term, we are going to be up and up. Now we can take one of these figures, we can take any of these pictures, and we can go ahead and flip it. So if we flip our entire picture, if we flip our entire picture, and it won't let me, but we could go ahead and draw this to where it opens down. And same thing for all the other ones. And if it opens down, then, well, we have this. All right, so those are all of my possibilities or examples of different possibilities for a quartic. All right, the next thing, we've got one more we're going to look at. We're going to look at a quintic. All right, the last one that we are going to look at is a quintic. And so a quintic, the first thing that we have is that it is going to be degree 5. Okay, now this is going to be the last one that we're going to look at because we're going to see that this one, there's so many possibilities. All right, so let's go ahead and look at some examples of graphs of quintics and see what we can determine about x-intercepts and turning points. Okay, the first one that we are going to look at is our basic quintic. And our basic quintic is going to look like this. It looks like a cubic function, okay? But just like we saw with our quartic, is when we look at a quintic, when we look at where it kind of comes in at the middle, is that, again, it's going to be very, very shallow, and then it takes off very quickly. All right, if we go ahead and move this around now, notice that no matter where I move this, it will always only have one x-intercept. So that's our first possibility. We can have one. Okay. For this, we have no turning points. If we look at our graph, we are starting at the bottom, we are increasing, and even though we get shallow, we never actually turn around and go back down. And then we take off again, and so we are increasing for the entire graph, and we have no turning points. All right, that's our first possibility. All right, let's look at another one. Another possibility is going to be this one. Okay, and if we look at this one, we have one x-intercept, we can have two x-intercepts, we can have three x-intercepts, and if we keep going down, we can have, again, 2 or 1. All right, so what do we say we have? We have 1, 2, or 3. And we also have turning points for this one. So if we look at our turning points, we have that our graph is increasing, levels out, and then it does go back down. So there is one turning point. And then it goes back up, and we have 2 turning points. All right, so let's add that to our possibilities. We said we can have 1, 2, or 3 x-intercepts. And we said for this one, we have 2 turning points. All right, that is that graph. Okay, let's pick another one. All right, the next basic shape that I want to look at is this one. Okay, if we look at this particular graph, let's see what we got. We can have one x-intercept, we can have 2, we can have 3, or again, we can have 1. And so we have that. We also want to know about turning points. Again, when we look at this, we are increasing, we level out, we increase again, so not a turning point. But if we come up to this top point and turn around, there is 1 turning point. We come down to the bottom and go back up, and so we have 2 turning points. All right, so let's see here. Nothing new to add on that one. Okay. All right, so now let's look at a couple others. All right, let's look at this particular picture. All right, if we look at this particular graph, okay, again, we can start off with our 1 x-intercept. We can have 2 x-intercepts. We can have 3 x-intercepts. We still got 3. We still got 3. We still got 3. We're down to 2. And then we're down to 1. And so from here, we saw that we can have 1, 2, or 3 x-intercepts. Okay, nothing new there. All right, but we also only have 2 turning points. Again, we have that our graph increases, keeps increasing, it goes up. This is a turning point. It comes down, we have another turning point, and so we can have 2 turning points. All right, so that's what we've kind of seen so far. And they all look a little bit different, okay, but we see that, we can either have 1, 2, 3 x-intercepts, or we can have 0 or 2 turning points so far. All right, now let's go ahead and look at last 2. All right, the next one I want to look at is this picture. All right, this is also a quintic. And so let's play around with this one and see what we can do with it. All right, if we started up at the top, we can have 1 x-intercept. If we bring it down, we can have 3 x-intercepts. If we bring it down further, we can have 5 x-intercepts. And as we continue to move it down, we can have, again, 3 or 1. Now, we do have something to add here. We do have a possibility for 5 x-intercepts. And we are also going to add some stuff into our possibilities for turning points. All right, if we look at this graph, when we look at this graph, let's see how many turning points it has. We are going up and then down. There's 1 turning point. We go down and then back up. There is another turning point. We go up and then back down, another turning point, down and back up. And so we have a total of 4 turning points on this graph. All right, so let's go ahead and add that to our possibilities. So here we saw that we can have 3. We have 1, 3, or 5 x-intercepts. Don't want to rule out the possibility for 4. And then we also saw that we had 4 turning points. All right, that is that one. We have one more possibility. Actually, we have several more, but I just want to look at one more. Let's bring this one over. All right, this is kind of like that last one, except for we don't have these points at the, we don't have our local maximums and our local minimums at the same level. All right, let's play around with this one and see what we can do. So we can again start our graph at the very top. Okay, we're gonna move the whole thing up. That's not what I wanted. Okay, we can start this thing all the way up, and we see that we have one x-intercept. If we bring it down, we can have 2 x-intercepts. If we continue bringing it down, we can have 3. Continue bringing it down. This one, we get 4. If one of these, if this middle one is on my x-axis, we have 1, 2, 3, 4. All right, let's keep moving it down. If we move it down a little bit more, we have 5. We keep moving down. We are back to our 4. If we keep moving it down, we have our 2. And if we keep moving it down, we have our 1. And so that is the last possibility that we're going to have. And if we also look at this, how many turning points do we have? We have 1, 2, 3, 4. And so those are our possibilities. So we are going to go ahead and add in that it is possible to have 4 x-intercepts. Now it is not possible for, when we talk about polynomials, and we'll talk about this in just a second, for, remember, odd functions, because we do have a a range of all real numbers, if our degree is odd, we will always have at least one x-intercept. But if you've noticed, as we've looked at all of these different examples, we do have a limit on how many x-intercepts we have in terms of our maximum number of x-intercepts. The maximum number of x-intercepts is going to depend on your degree. If it is a degree 5, the most x-intercepts you can have is 5. But if you notice, we have a lot of possibilities. Notice that we had pictures here that had 1 x-intercept, 2 x-intercepts, 3, 4, and 5 x-intercepts. And so it's hard to determine, okay, well, given an equation, how many x-intercepts does it have? That's a little bit harder, okay? And we will talk about how do we find these later on. The last thing that we do want for this particular slide is let's go over our leading term and our in behavior. So again, our leading term can be positive or negative. And all of the graphs that I drew did have a positive leading term. And so just like we saw with all of our odd degree polynomials, is it goes down forever on the left, it goes up forever on the right, if our leading term is positive. If it is negative, it's the exact opposite. We can take any one of these pictures that we have drawn and we can reflect it across the x-axis. And what we're going to end up with is it goes up forever on the left and down forever on the right. All right, those are our examples. And now we want to go ahead and wrap this up in terms of what did we find out. All right, so if we are given a polynomial function with degree n, where n is greater than 1, then what we have, and this is about all that we can say about it, is we have at most x-intercepts. If you have a degree 7 polynomial, you will have at most 7 x-intercepts. Now we also have turning points. And this is the one that we kind of focus on a little bit more. Because remember that, we had graphs that could have 1, 2, 3, 4, 5 x-intercepts. But we did have a little bit more restrictions in terms of how many turning points we could have. But our general rule is that depending on the degree, we subtract 1 from it. And that is, again, at most, that many turning points. So if we have a degree 8 polynomial, I know that I can have at most 8 x-intercepts, and I will have at most 7 turning points. Remember that number of x-intercepts is also dependent on how many real solutions. And we've talked about real and complex. When we have a real x-intercept, we do have if we have a real solution, it does correspond to an x-intercept. But if we have a non-real complex solution, we have them in pairs. And those result in those turning points that either approach but never actually get all the way down to the x-axis. All right, that finishes off this particular presentation. Now in the next presentation for this section, we're actually going to look at some examples and try to figure out the information that we want based on the equation alone. We are not going to look at any graphs, or we are going to try to match graphs with equations based on this particular criteria. All right, I will see you again shortly. We are done with this one.